Today I will talk about a very special topic for me, which is online experiments and A/B testing. It basically is a marriage between classical statistics and big data, and I believe it's very relevant to modern age software industries because all new features are being tested through the same procedures. And I have collected various topics related to it, and I will reference to modern literature. And I guess it's going to be informative for you. Yeah, so to start from a lightweight, funny part, imagine a fictional story of a person who is concerned about his mobile application. So this story is about Garnik. He owns a mobile application called Cheap Sheep, and it's a mobile application selling care products for sheep, and yeah, he's concerned about his sales. Yeah, these are the ratings. Yeah, evidently he's not very famous. Okay, in terms of reputation. So what Garnik thinks that will solve his problems. He hires a data scientist apparently and a designer. So the first thought that comes up to the designer is to see the current page of his mobile application, and he sees this. And yeah, apparently this is perhaps not the best way to showcase your product, and he suggests to change it to a new version, to a different design. And the evident question comes up whether we can just basically replace the old version with the new one. And then the scientist denies and suggests that we can actually conduct an experiment and test that feature's performance. And the procedure whereby we can do it is the A/B tests, which are basically the history coming from the experiments are dating back from the 20th century, where they were already researching how to do clinical trials, testing new drugs, and basically the inspiration of online experiments is coming from the test of drugs. But in this case, our drug treatment is the new feature or a new design of a mobile application. But to have such experiments, we need to make certain assumptions, and the primary assumption is the randomization. Well, by randomization, we mean that we have to randomly assign two groups of people into control and treatment groups, where the treatment is actually the new feature we are testing against the baseline control, and the control is basically the old version that the users were already exposed to. And if we create all other things equal setting for those versions, we can actually attribute the effects to the treatment itself rather than some random effects that are by chance. So we are also going to assume that we are working within certain set of assumptions in terms of our scientific method, which is FREQUENTIST framework, which I will introduce in future. And also we assume that the treatment does not affect the participation, which means basically the fact that you are going to take the drug is not because you were exposed to it, but your choice to see the new product is not because of the treatment, but because it's basically it should be the same distribution across both groups. And also we believe that participants cannot see other versions and they do not interact with each other. Yeah. And the rough the structure of this presentation is going to be as follows. So we will start from metric definitions, the design of experiments, and the analysis. Okay, so, but before we jump into the first chapter, it's important to specify why we care about the randomization. And as I mentioned, we need to have this all other things being equal setting. So the only thing that is different is the treatment itself. Also, we assume that the observations, in our case the users that were exposed to the experiment, are independent of each other. Okay. And for those ends, we have various sanity checks that we can perform before each experiment, which has the issues of randomization. There's literature referencing to it, and also there's issue of flickers, which are basically users that own multiple devices, and they can be assigned to different experiments because they have multiple devices. And we can sometimes not identify those cases, but we have to be careful. Well, what is the reason that we care about experimentation is the notion of external validity. It basically suggests that if we observe an effect during our experiment, we want those effects to be repeatable and generalize the larger behavior of our population. And that's why we perform experiments. And there are a variety of factors that violate these assumptions. So if there is some seasonal change or users are having change aversion behavior, basically they are not liking the feature at first, but they might like it in future, our analysis might be a little biased. And there are other cases like outliers in our observations, and there are various treatments for those. Okay, and definitely if we randomize, we have to choose a randomization unit. And by randomization unit, we mean the units that we are going to randomize with. And in case of mobile application, a good choice is device ID, because a lot of users are not registered. And so the way to identify them is the device ID. And even though we randomize by the device ID, we don't consider all devices as our participants. And as this diagram suggests, we have to make sure that the device was actually exposed to the new feature. So we can assign the user to the experiment, but unless the user actually sees the new feature, we cannot consider the user as our participant. And yeah, we can jump into metric definition. Yeah. Okay, so metrics should be good indicators of the new feature's performance. So if we show a new screen, as in case of ChipShip, we have to make sure that that new feature is actually better, and metrics are the way we can compute it. So I guess I can ask the audience, like, in your opinion, what can be a good metric in case of the new screen that we have shown? Yes. And how do you measure it?
It is like easier to navigate to the screen zone. It is easier to reach the content.
Yeah, the answer was we should measure the user experience, but yeah, we have to specify the actual way we are going to compute it, like through clicks or other measures.
Yeah, through clicks is good.
Okay, I guess so too. So yeah. We can basically compute the average number of purchases between two versions, and that already we basically maximize the profits. So therefore, we care whether we have more income in the first version or the other one. Another thing is the user engagement, which can be computed via retention. So if the more users are retaining to your application, if you introduce a better UI, then it means it's superior. And we can have many of such metrics. They can be funnels, ratios, like purchases over page views, and other ones. And also, to just briefly introduce the FREQUENTIST framework, we believe that the hypotheses are independent of the data. This is important because we usually think we should generate the hypothesis from the data first, but if we do so, we have to test it on a different set of data because our assumptions will be consistent with the observed ones, but we are not sure whether they will be consistent with the new set of data. That's why ideally we have to just assume that these hypotheses are beneficial for us and then test it through the data. Also, there are unknown parameters that we are testing, which we believe are constant and they are not random, but we don't know. We can never know them. We can only estimate those, and our estimations are definitely random. And the interpretation of probability is seen as proportion of successes in infinite number of trials. So, for instance, the probability of winning poker is basically, if we play it like infinite number of times, it's the proportion of our wins, basically. Yeah. And a more rigorous formulation for the case of clicks can be done in the following way. Basically, we believe there are two distributions, data generating distributions, that give rise to the clicks. So yi is basically either 0 or 1. So in the case of click, it's 1. And we believe they are coming from the same distribution. And the unknown is the probability of the click, which is the pi underscore c. So the difference between yi and zy is basically, one is the clicks under control and the other one are the clicks under treatment. And the probability mass function for the distribution is defined as following. So basically pi t is the probability of a click, and the outcome for not clicking is basically 1 minus pi t. Same applies for the control. Yeah, it's pretty straightforward, but even though we have two unknown parameters, which is pi c and pi t, we are actually only interested in the difference. And yeah, so by the difference of proportions, we mean basically the probability of clicking under treatment versus probability of clicking under control. And if this difference is different from 0, we claim that we have an effect. But it works in the following way. We usually assume that our assumption that there is no effect is true, and if we find any evidence against this hypothesis, we reject it. And even though these parameters are concerning the population, we can only observe a sample of users. So that's why we are working with estimators, and a reasonable way to estimate the probability of the click is basically the proportion of clicks out of our participants. And as we compute those proportions, their difference estimates the population parameter difference. And are all metrics good? So a natural question arises. We define it in the following way. So if our metric is sensitive, meaning that if it responds to the change when it actually exists, we consider the metric as sensitive. Whereas we also believe that the metric should not respond to the changes when they don't exist. Like in the case of AA tests, where we actually randomize to the same version, and we believe there should be no effect if the metric is doing its job well. There are other desirable properties from a theoretical perspective. For instance, the metric should be unbiased, meaning that on average it should predict the parameter well, and other things like its variance should be small, like in the case of efficiency. And there is like merger of these different properties, which is the UMVU. And from literature, we just know that the difference of proportions is UMVU. Basically, it has many good properties, because of which we can believe this metric. Yeah, so I guess this is it for the metrics part, and we can jump into the design. So what do you believe what do we mean by the design of experiments, in your opinion? Any thoughts? Okay. All right. Yeah. So, okay, I will introduce it then. So, but before we introduce the design of experiments, there are two important notions. The first one is the errors that we can make, and of course, any scientific experiment contains various errors, and we cannot live in the perfect world. So, the first type of an error that we can make is called type 1, and it basically suggests that we claim that we have detected an effect, but actually there is no effect. So we just detected an effect by chance, and we only allow it to be around 5%. So, and this is a bad type of an error because it is a false discovery, which we want to definitely avoid. Another type of error that is usually less costly is when we miss the discovery. So, and it controls by the type 2 error, which basically says that we do not claim we have an effect, but we actually do have one. And the design of an experiment is concerned with questions like number of days to run the experiment, sample size, allocation, percentage. And we are usually looking for the smallest sample size possible, because if we can make an inference at a shorter time with the shorter amount of people, it will save us a lot more time and costs. So we definitely prefer the smallest possible sample. And the way to make sure that the sample we have collected is enough for our inference is the power analysis. And we know that power, which is basically the 1 minus the type 2 error, is positively correlated with our sample size that we have observed. So if we have a lot of participants, we are sure we have high power. It means that we are not going to miss a discovery when we actually have when we actually should discover it. And also, it's important to know when you are stopping the experiment. So you cannot stop it randomly. You cannot stop it randomly after looking at the data. You have to know the exact rule by which you're going to stop it, and the best way is to stop it when you collect the sample size needed. So as you perform the power analysis, you will know ahead of time how much sample you need. Yeah. By the way, if there are any questions, meanwhile, you can ask those. Yeah. And the intuitive equation for the design is the following. We definitely know the participation rate ahead of time, which basically is the probability of coming and viewing the page where you introduce the new feature. And also we know on average how many users are entering your application. And we estimate the sample size through the power analysis, which I will show in next slides. But we don't know is the allocation percentage of the traffic. So basically, it's the proportion of users that we are going to assign to the experiment. And we also don't know how much we are going to run our experiment. But as we have our estimations, we can play with this equation and come up with the most appropriate solution for our needs. So this basically means that out of certain traffic, we know how much will participate, and from that participants, how much we want to allocate to the experiment. And this is basically daily granularity, and that's why we also multiply by the number of days we're going to run the experiment. And this should exceed or be at least equal to the estimated sample size. And to compute the sample size, we have the power analysis procedure itself, which has this parameter space. We first have to fix the alpha and beta errors. It's usually 5% for type 1 error and 20% for type 2. So we are more okay to miss a discovery rather than we have a false discovery. And also we should, from our business knowledge, we should define the minimum effect that we care about, which is the minimum detectable effect. And we also know the baseline conversion rate. And to estimate the sample size is basically to solve the equation with these parameters that will guarantee at least 80% power. So if your beta is 20, then you're looking for 80% power. Just a simple example. For instance, we have done some exploratory data analysis, and we observed that out of 1,000 page views, 100 converted. Click the button, for instance. And we care only, the minimum amount of effect that we care about is 2%. So basically, if it's less than 2%, then we are okay to miss the discoveries. And there is online calculators that can do this for us, and it suggests that if we collect around 4,000 participants per variant, our inferences will guarantee 80% power. And yeah, some properties of these estimations are the following. If your baseline conversion rate is very low, you need a lot more participants to prove that you have an effect. Also, if you are only care about large effects, you need a smaller sample size, because if the effect exists, it will be present in the small sample sizes as well. And if you reduce the type 2 and type 1 errors, you need more observations. Okay, so of course there are various ways to compute these sample size estimators, and there's literature referenced. But a natural question arises: what if it will take forever to collect the sample size needed? And there are some various solutions to this from modern literature, as referenced here. And also, can we actually peak during the experiment? So ideally, I told you that we have to wait until the experiment terminates and then we look at the numbers, but we usually do look at the numbers meanwhile. So, and there are really clever ways to do so, which are continuous monitoring experiments, and it's extensively researched in modern literature. And yeah, as we have collected our metrics, we know the design and the sample size needed. We can jump in to the analysis part. Okay, so a little history here. Well, the formal way of doing experiments was created in the beginning of 20th century, and the first one to formalize it was Ronald Fisher, and he suggested the uses of p-values, which I will introduce. But he was against the notion of type 2 and type 1 errors, and that's why, meanwhile, his opponent scientists were Neyman and Pearson, who suggested alternatives to the procedure. And to find a middle ground among these debates, scientists created the notion of null hypothesis significance testing, which uses all of these notions in one single framework. But in modern applications, we usually use the p-values for the rejection, and we also report the confidence intervals to summarize variability. Yeah. So, what do we mean by the p-value? It's basically a way to summarize the evidence against the null hypothesis. So we usually assume that the null hypothesis is true, just like in the court trial. If we find any evidence suggesting otherwise, we reject it. And the classical definition says that it's the probability of observing something more extreme or equal to what you have already observed. And under your assumption, if it's very small, then we reject the null hypothesis. Another way to approach it is basically the smallest type 1 error for which you can reject the null hypothesis. And the rejection criteria for this is basically when your p-value is smaller than your alpha, which is the type 1 error. And okay, so when we work with this algorithm, from the frequentist perspective, we are suggesting the following story. So if we repeat the experiment many times, it will be correct 95% of the time. So each time we claim we do have a significant effect, we are not sure whether we are making an error or we are telling a correct thing, but we don't care too much because we know it works majority of the time. So if it's 5%, then it works correctly 95% of the time. And as we define the p-values, we need a generic way to compute it for various metrics. And there are a number of ways to do it. And one approach is the central limit theorem. It suggests that if we have observations from any distribution, their averages will converge to normal distribution, basically the standardized average. And it basically means that if we have observations from any distribution, we average it and keep it into a box, and we repeat it many times, the distribution of those observations is going to be normal with 0 and 1 parameters. So basically we can construct the distribution of the null hypothesis for any metric using this asymptotic property. And the specific p-value for the clique cases that I mentioned is the following. So we can see that there is an expected value term here, and under null hypothesis we believe it's 0, so there is no effect. And we only are left with the first term, which is the average. In our case, the difference of averages. And we divide it by the variance of the metric, which is called the pooled standard error. And to compute the p-value, we only need to integrate over the tails of our observed observation, basically the z, which comes from the normal distribution. So basically we can compute the p-value for many metrics using this same formula, where z is the small case z is basically the point of is the percentile under the standard normal. And yeah, so we can compute it this way. And after we know how to compute the p-value, we also need to summarize the variability of our metric. Basically, if we observe, for instance, 0.2 difference, whether we are going to observe the same thing as we repeat the experiment. And for that, we have the notion of confidence intervals, which is basically a random interval containing your parameter at the rate of 1 minus alpha. So it can contain the parameter 95% of the time, if it's 5%. This is the formula for the case of proportions. So the right term quantifies the uncertainty about the metric. And this is a specific example. So if we have done power analysis, we randomized, we know that in each version we have 100 participants, and the clique proportion in the case of control was 0.46, and the treatment group has 0.62. The difference is 0.16. And from the confidence interval, we can notice that this difference can vary, and it can be from 0.02 up to 0.3. It means that we actually need more sample to make this interval shorter, and we might not completely trust our results. But from the p-value, we can notice it's really small, so we actually can reject the null hypothesis. Yeah, and as we have rejected the null hypothesis, we made sure that external validity is set. We also need to make sure that the effect observed is actually practically significant from the business perspective. So, and which usually comes from the minimum detectable effect that we have talked about. And we need to make sure that the lower bound of our confidence interval should exceed it. And then we can claim we have a practical effect. There are other approaches, more specifically non-parametric approaches, which have less assumptions and are more computationally heavy, but they are pretty straightforward in terms of their use, and they can provide the same significance testing in an algorithmic manner. And this is actually a good visualization that I would like to show. There are other approaches to causal inference. So actually there is another term that we can use. So as we detect an effect during a randomized experiment, we claim we have causation from the treatment. And the classical way that Fisher was doing 100 years ago is the ANOVA. And it still is the gold standard in the case of clinical trials to prove that drugs work. I definitely recommend to read some literature on this. Some additional issues that are worth mentioning. As we have many metrics that we are testing for, we actually inflate the type 1 errors. So, and there are two ways to quantify it. So, first approach would be the probability of at least one false discovery, which is basically if we have 10 comparisons, it's actually 40%, not really 5. So to correct for this family of comparisons, we need to actually reduce the alpha rate, and one way would be to divide by the number of comparisons. But if we do so, we are going to be very conservative of the null hypothesis, and that's why the FDR, which is the expected proportion of false discoveries under rejected tests, is a little less conservative and is a better approach in the case of industry applications. Yeah. Okay. Another huge issue is the selection bias, which we kind of talked about. It's basically when we are actually having many questions, but we only choose to report a subset of the numbers that we have observed, and basically pay attention to the most interesting things that are favorable of our hypothesis. And it's ongoing research. There are many approaches against these biases. And I guess this is mostly it. There are many references to the literature. Yeah, I also want to thank my team for making my experience possible working in this field. Also, credits to the designers of the presentation. They did a lot of work. So yeah, basically, I will try to open the visualization. If we fail, then we'll jump to questions. So it was here. Okay, I guess I can just search it. Should I be signed in to open this? Or?
Just click on the Barcamp.
Oh, okay. This one? Yeah. So let's try again. Okay, it works. Okay. So this is a non-parametric way of computing null hypothesis for this specific example. So these are basically a shepherd wants to test the quality of a new shampoo, and the only metric that he tests is the quality of the fur. And what he believes he should do is basically to randomize the sheep, or in this case, they are llamas, and he tests this for the quality of the new shampoo. But the algorithm works in the following way. So if we assume that the null hypothesis is true, it means that there is no difference between these llamas, whether or not they were treated. So he Fisher suggested to permute those llamas, basically to swap them infinite number of times, because there is no difference, right? So we can actually replace their place, exchange them, basically shuffle them in multiple ways. And as we shuffle, we can compute the differences of average quality under the first shampoo and the average quality under the different shampoo. And each time we can plot these observations. And if we do this many, many times, we will have the exact distribution of the null hypothesis. And what we should do is to measure the p-value, which is basically the probability of observing something more extreme or equal to what we initially observed. And if this probability is low, then our initial assumption was wrong and we have to reject the null hypothesis. And this is just another way to approach it. And yeah, I guess this was it. Okay, thank you. Yeah, I'm open to questions, I guess. Yeah. So, are there any questions? Okay. I guess if there are not any, then I will finish. Thank you.